Hi, everyone. Welcome to today's lesson on boundary behavior and interference. We're going to be looking at what happens when a wave or a pulse encounters a boundary, and what happens when two or more waves or pulses collide with each other, interfere with each other. So let's start with boundary behavior. So first off, a boundary is where one medium ends and another begins. The medium being the substance that the wave is traveling through. When that medium becomes a different medium, then that is where we have a boundary. And so boundary behavior is what happens when a wave encounters that boundary, that change from one medium to another medium. And we're going to look at some simple examples. We're going to look at a wave on a string, and we're going to see what happens when it encounters a boundary with a loose end. And then what happens when it encounters a boundary with a fixed end? What happens to the reflection of that wave? And you've seen all this in the lab, so this is more of a summary. So let's take a look quickly here at what happens when it encounters a loose end. We can see here how it might be a loose end is a ring attached to a pole. And so this string here, we're going to be able to send a pulse, a wave pulse down this string. And when it gets to the pole, it will, the ring here is allowed to freely move up and down the pole. And then we'll see what type of reflection that we get with this boundary behavior. So let's send a pulse down. And we see it's an upright wave. It encounters the boundary. I'll move my picture here. Encounters the boundary. Let's just watch it when it's upright here. So it's upright. It encounters the boundary. It reflects upright. We can see that in slow motion. It's upright. We notice the ring goes all the way up, and then it comes back down, and the wave reflects upright. So let's write that down. We have the incident pulse. Incident pulse being the pulse coming in. Could have an incident wave, but the wave coming in to the boundary. And that looks maybe something like this. Here's a very basic example. Here's a wave pulse, and here is our post with the ring attached there. So that's our loose end. And we have a wave moving inwards. And then the reflected pulse, it's going to be in the same orientation. It's going to be the same wavelength, and in this case, even the same amplitude, same wave speed. We'll talk about that shortly, but it's coming back in the opposite direction. Whereas for a fixed end, and a summary for loose end then, if we have an upward pulse, it's going to reflect upwards. If we have a downward pulse or an inverted pulse, it's going to reflect inverted. For a fixed end, well, let's remember what that looks like. For a fixed end, we're going to have a wave pulse coming in. Let me restart that. And we see that we have an upward pulse, and it hits the boundary, and it reflects inverted. An upward pulse hits the boundary, reflects inverted. Let's watch that in slow motion. We can see that all the energy kind of encounters the boundary and then flips around. So let's draw a quick picture of that. We see the incident pulse, an upright wave encountering a fixed end, so attached to the pole. The reflected pulse is going to be inverted, moving back in the opposite direction. So an upright pulse is going to reflect inverted. An inverted pulse or a downward pulse is going to reflect upright. So here's some notes about reflection. The speed of the reflected pulse is going to be the speed of the incident pulse. The reflected pulse is going to be traveling at the exact same speed as the pulse that was coming into the boundary, because both of those pulses are moving in the same medium. And we remember that the medium is the only thing that determines how fast a wave is moving. And so because it's in the same medium, it's going to have the same wave speed. The frequency is going to be the same. This is a little trickier for pulse, because a pulse is just a single wave. But if we were to have multiple waves coming into a boundary, if we were to have 5 waves per second hitting a boundary, 5 waves per second would be reflected off that boundary. The frequency would be the same. And then because of both of those being the same, the speed and the frequency being the same, that means that the wavelength has to be the same, because the wavelength is related to the wave speed and the frequency from that wave equation. The wave speed is equal to the wavelength times the frequency. They're related to each other. And so because the speed and the frequency are the same, the wavelength is also going to be the same. Now, the one thing that might change is the amplitude. And in fact, in a real life scenario, the amplitude would definitely decrease. In the scenarios that we just saw there, the amplitude did not decrease because those are ideal scenarios, meaning we've gotten rid of damping, we've gotten rid of any other friction, any energy transfer outside of the system. But in a real scenario, if a wave was to hit a boundary, there would be some transference of energy into the new boundary. It would not all be reflected. And as a result, the amplitude would decrease. The reflected pulse would have a decreased amplitude. And this is because the amplitude of a wave is an indication of how much energy that wave is carrying. Which means a wave with a big amplitude is carrying a lot of energy, and a wave with a small amplitude is carrying a small amount of energy. And so if a wave encounters a boundary with a big amplitude and it rebounds, it reflects, and it has less amplitude, that means that it has less energy. Some of that energy went into the new medium. Okay, let's now talk about wave interference and superposition. So wave interference is what happens when waves or pulses traveling along the same medium, they encounter each other and they overlap, they interfere with each other. And we're going to talk about the two types, constructive interference and destructive interference. So constructive interference is when two waves have the same orientation. It means that they're both upright or they're both inverted and they interact with each other. So we saw this in the activity. It looks something like this. And when we run this, we see when they have the same orientation, they're both upright, they stack up. The other thing that we notice is that the waves travel through each other. They don't bounce off each other, they travel through each other. And the last thing that we can notice is when they stack up, I'll pause this at just the right moment. I'll just scrub ahead a little bit. When they are totally overlapped, the height of the superimposed wave, the two waves combined, is equal to the sum of the heights of the individual waves. This one has a height of 2, this one has a height of 3. The total wave height is 5. So if we have a wave, I'm going to draw some colors here. Let's say we have a blue wave and a red wave, and they're moving towards each other on a string like this. Blue wave moving this way, red wave moving this way. When they collide, when they completely overlap, we have the blue wave and we have the red wave overlapping each other. Sorry, my art is not perfect. Something like that. When they overlap, the resulting wave, blue and red, is, let's turn that into purple. The resulting wave, yes, this is our resulting, or I guess this is our pulse, is just the stacked up version of those two. And then afterwards, these two waves, they travel through each other. They do not rebound off each other. They travel through each other. So they move off in their opposite directions, the same directions that they were originally traveling. Blue moving to the right, red moving to the left. And now for destructive interference, this happens when we have two pulses or waves that have opposite orientations, different orientations, one upright, one inverted, in whatever way you want. And so looking at that, we see we can change this one, maybe this red guy here. Let's run this so that they move away from each other. So we have one guy that has downward height and one has an upward height. And when we run them, we see that the resulting wave, and it's a little trickier to see it here, but if we pause it, we can see, gotta try that one more time. We pause it. we can see that the overlap of these two waves, when they perfectly overlap, the resulting pulse, there we go, something like that, is smaller. It's the subtraction, the difference between these two pulses. So this blue pulse has a height of 3, the orange pulse has a height of -2, and so the combined pulse 3 plus -2 is 1. All right, so they cancel each other out. They destruct. It's called destructive interference. They destroy each other, in essence. And a special case of this is when they have the same height. I'll even bring this all the way down to -3. Run this again, and I'll pause it. We'll get all the way to when they're totally overlapped. We see that when they're totally overlapped, they completely destroy each other. The resulting wave pulse is no wave at all. All of positive and the negative has completely canceled each other out. But when we run it again, they continue on their individual ways. They don't stop moving in the direction that they were originally moving. Okay, so let's draw that, and then we'll do a little bit of math here. So if we have a positive wave pulse over here and a negative wave pulse over here, and they're moving in their respective directions, blue to the right, orange or red to the left, then when they overlap each other, we have red downwards, we have blue upwards. We'll get some, let's just imagine that these are the same. Our resulting wave would be the subtraction of these two. And then they will move off in their individual directions. Okay. And all right, so let's do a couple examples, and these are pretty simple examples. So if we have a wave pulse with an amplitude of +5 centimeters and it collides with a wave pulse with an amplitude of +7 centimeters, what will be the resulting amplitude when they are overlapping? So here's our 5, and here's our 7. And when they overlap, we're going to get an amplitude that is the combined, right, our amplitude being the height from the midline here. Our amplitude is going to be +5 plus +7, and that's going to equal to +12, positive 12 centimeter height. Whereas if we have a wave pulse with an amplitude of 20 centimeters, positive 20 centimeters, and it collides with a wave pulse with an amplitude of -25 centimeters, I'm over exaggerating just to show the two heights. When they combine, we're going to end up with a wave height. There's more wave downwards, so we're going to have a really small amplitude here, and it's going to be negative. The amplitude is going to be +20 plus -25. We're going to have a -5 centimeter wave height. It's as simple as that. Okay, that's it for today. And I will see you in the next video.